Good morning, class. Welcome to the chapter 4 of our probability and statistics class. For this lesson, we're going to discuss about estimation of parameters. Very often, we want to describe particular characteristic of an entire population. The information might be needed for decision making. However, collecting data from the population is impractical even if it is possible to do so. So researchers often use a random sample to undertake this. The results may not exactly be equal the population parameter, but there are acceptable procedures to approximate population values. The process by which conclusions about parameters in the population are made based on the sample data is called statistical inference. In statistical inference, there are two areas. The first one is the estimation, and the second one is the hypothesis testing. Our topic for our first lesson is computing the point estimate of a population mean. And our objectives are understand the concept of estimation, to distinguish between point estimate and interval estimate. And lastly, find the point estimates of population means and proportion. In real life, most of the information we deal with are numericals. When we wake up in the morning, our first concern is the time, be it a number, example, 6 o'clock, or a word, example, early in the morning. Between the two expression, which would you prefer? And why? Why do you think so? So, for our example number one, let's try to collect information about the wake up time of every person in our class during school days. So, we need to represent each information by a tally mark. Then count the tally marks and write corresponding decimal numerical under the heading frequency. The question is, what is the average wake up time of your class? So let's try to figure this out. Let's say, for example, we have 30 students in a class, and the class will start at 8 in the morning. So we collected data from there. So we have 8 who wakes up at 5. We have 3 for 5:30, 5 for 6 o'clock, 7 for 6:30. Then for 7 o'clock we have 8 students. And lastly, for 7:30 we have 2 students. So maybe the students that wakes up at 5 in the morning is far from their school, and then 7:30 they are just near or in front of the school. So the frequency will be for 5 a.m., it's 5. 5:30, that's 3. 6, that's 5. 6:30, 7. And then for 7 in the morning, it's 8. And for 7:30, that's 2. That will give us a total of 30. And to know the average, we need to solve 30 divided by 1, 2, 3, 4, 5, 6 by 6, which will give us an average of 5. Therefore, the average wake up time of your class is 5 in the morning. The arithmetic average computed from our table is known as the mean. The class constitutes as a sample. So if we repeat the activity to, let's say, 10 random classes, then we obtain 10 arithmetic average or means. Suppose we proceed to compute the means of the means for all 10 classes. The final result is a number that we call point estimate of the mean mu of the population where the samples come from. So in symbol, we write this as the mean of the mean is equal to the population mean mu. Okay? So we recall that parameters are numerical descriptive measures of population and they are usually unknown. However, we can estimate population parameters from same values. So in statistics, sample measures such as the sample means and standard deviation are used to estimate population values. Here are the terms that we encountered on our example. So first, we have the estimate. Estimate is a value or a range of values that approximate a parameter. It is based on sample statistics computed from sample data. We also have the estimation. Estimation is the process of determining parameters value. Point estimate is a specific numerical value of a population parameter. The sample mean is the best point estimate of the population mean. We also have the interval estimate. It is a range of values that may contain the parameter of a population. So if we remember, the means of the sample mean approaches the population mean in symbol, we write this as the mean of the means is equal to the population mean mu. Let's have another example. Susan, a TLE researchers, look at the average time in minutes it takes a random sample of customers to be served in a restaurant. From 40 customers, the following information was obtained. So what is the average wait time? So first, what is the mean of the sample in minutes? Second, this value is called what of the population mean mu? Third, based on the observation of the mean, would you patronize the restaurant? So here we have this table. And if we're going to get the sum of this, it will give us 500 minutes. And then to find the mean, we need to divide 500 minutes into 40 customers. So therefore, it will give us a mean of 12.5. And the mean of the sample is an estimate of the population parameter mu, the true average time it takes to be served in the restaurant. So the number is used to describe a particular characteristic which we called wait time of the population. Okay, so the mean of the sample is 12.5 minutes, and this value is called the wait time of the population mean mu. If indeed this is the average time it takes to wait to be served in that restaurant, would you like to dine in that restaurant? So your answer to this question is a decision based on the observed wait time of the population. And a population can be finite or infinite. An infinite population is countable. The actual number of customers served in a restaurant constitute a finite population. And an infinite population is a hypothetical collection of elements, such as all the results of a tossing coin experiment to determine the probability of getting heads or tails. A population parameter are usually unknown fixed values, but there is a way to determine them. In the example we have on a previous example, there are two ways to report the results. So first, report a number that describe the average wait time. So this number is called point estimate. So we already discussed that on our previous slides. So in this case, the mean is the best estimator. So we were going to question why not the median or the mode? Among the three measures of central value, the mean is the most reliable measure of center. In a mean, any change in a value affects the result. Mean of samples vary less than the median or the mode. So another way to determine the population parameter, which is we already know that our unknown fixed values, is to report a range of values that contains the number that truly describes the wait time. So this number is called interval estimate. So remember, we have two kinds of estimate. So first, we have point estimate, and next, we have interval estimate. So that we're going to discuss on our next lessons. Okay? So a point estimate is a specific numerical value of a population parameter. The mean, the sample mean is the best point estimate of the population. An interval estimate is a range of values that may contain the parameter of the population. So estimates provide limited information. Okay? It does not tell about the information, and it does not tell much about the possible size of the error. We supplement the information by stating that the sample is a random sample. Again, in our example, we have a random sample whose mean is 12.5 minutes. Okay? And if we compute for the standard deviation, it will be 3.41 minutes. The sample standard deviation can serve as the estimate of our sigma, or our standard deviation. Okay? So we can ask, how confident are we about our estimations? So in order to feel confident about the estimators as approximation of the true parameter values, we take as many samples as possible from the population of interest. So we compute the sample statistics and then carefully compare the results. Then we formulate conclusions, and based on this, we make particular decisions. A good method of estimating a population parameter is described as one where the estimates from many samples are equal to the true population parameter. In such cases, we can say that the sample statistic is an unbiased experiment. If across many samples, a sample statistic depart from the true population value, then the estimate is said to be biased. There are two properties that describe a good estimator. First, when the mean of a sample statistic from a large number of different random samples equals to the true population parameter, then the sample statistic is an unbiased estimate of the population parameter. Second, across the many repeated samples, the estimates are not very far from the true parameter value. The following figures illustrate bias where the vertical line represents the population mean and the dots represent sample means from the mean of the sampling distribution. So here we have the negative bias or underestimate, unbiased on target estimate, and positive bias wherein overestimate. So if you can see again, the vertical lines represent your population mean and the dots represent the sample mean. So you can see here in the negative bias, most of the dots are on your left side. Okay, and for the unbiased, we have an equal distribution of your means. For the positive bias, we have here the means are on the right side. Let's have this example to understand what I'm saying better. Okay, so Mr. Santiago's company sell a bottle coconut juice. He claims that a bottle contains 500 milligrams of such juice. A consumer group wanted to know if this claim is true. They took 6 random samples of 10 such bottles and obtained the capacity in ml of each bottle. So the result is known as follows. Okay, assuming that the measurements were carefully obtained and that the only kind of error present is the sampling error. What is the point estimate of the population mean? Okay, so for the we have 6 examples, and these are the means. Okay, so let's try to do it in Excel. I already encoded the data in the cell proceeding from cell A1 to your cell A10. So your column A will be your sample 1, column B, sample 2, column C, sample 3, column B, sample 4, column E, sample 5, and lastly, column F, your sample 6. There are different ways on how do you compute for the mean. Let's start with this sample 1. So, we can write average, okay? And then from um, cell A1 up until to cell A10. So, Excel will automatically give the average. Another way on how do you compute the average is highlight from A1 to A10 and then go to your home tab. On the editing side, you can see the average. And it will automatically give you the average. If you go to the insert function dialog, you can also see that the formula is the same, which is average from your A1, cell A1, up until to your cell A10. And to compute for the other means of your samples, we just need to highlight this and then drag it all the way to your column F, and it will automatically give you the average of your samples. Now, how do we compute for the overall means? Okay, we just need to, like we did earlier, we need to write the average, and then from your cell A11 up until to your cell F11. Okay, so therefore, and then if we're going to round this off to two decimal places, it will give us an overall means of 496.33. Okay, so this is also the point of our estimate mu. The other way of computing or getting the estimation of the population mean is doing it by manual. So for the sample one, we need to compute for the mean. Okay, let's put it sample 1. So that will be 500 plus 498 plus 497 plus 503 plus 499 plus 497. 497 plus 497. So we have 7,497. 4 plus 498 over 10, because we have 10 samples, okay? And it will give us 4,980 divided by 10, and um, the result will be 498, meaning the mean of your sample one is 498, which when we go back to your Excel, it will also give us the same answer. Okay, and you need to compute for same process. You need to compute for sample 2, sample 3, 4, 5, and 6. And then to get the overall means, again, you simply need to simply find the sum of the means value. So you need to add all the means and then divide it over the total number of sample means. We're now on our lesson 2, that is understanding confidence interval estimates for the population mean. Our objectives are: first, define confidence level; second, define confidence interval; third, apply the normal curve concepts in computing the interval estimate; lastly, compute confidence interval estimate. So in our first chapter, we already learned about parameters. Now, when we describe population values, we want to be confident about our estimates. Other than the point estimate, we may use a range of values. So this range of values is called interval estimates. So what is interval estimate? It is called confidence interval. It is a range of values that is used to estimate a parameter. This estimate may or may not contain the true parameter values. Okay, let's say for example, the age of a beginning grade 1 pupil is any value between 6 years old and 7 years old. So, in determining an interval estimate, a degree of confidence expressed as percentage, such as 95%, that the interval contains the true and fixed parameter is made. That is, if we collect several random samples and then calculate a confidence interval from each samples, these confidence intervals are constructed wide enough so that 95% of them contain the true population parameter and 5% do not. The value 95% is also known as the confidence level. Okay? So the confidence level of an interval estimate of a parameter is the probability that the interval estimate contains the parameter. It is also describes it also describes what percentage of interval from many different samples contain the unknown population parameter. There are three common use confident intervals. We have 90%, 95%, and 99% confidence interval. So, along the way, we're going to know that the shorter intervals are more informative than the longer ones. And a short confidence interval can obtained by having a large sample or by using a lower confidence level. Okay, so let's try to have an example with regards to the 95% confidence level. Suppose we want to know the true average weight of all students in the population where the students in a class belong. We can increase the precision of our guess by getting as many random samples as we can from the population where the students purportedly come from. So, for example, we form five groups and we name it from group A up until to group E. And then we're going to assume that these groups are random samples. So, from this activity, we're going to use the 95% confidence level or 95% confidence. So each group determines an interval estimate of the population mean weight where the members of the group belong. Okay, so in a similar manner, if a large number of random samples resulting in more interval estimates were obtained from the population with mean mu, where the students belong, and our confidence level is 95%. Then 95% of these interval estimates will contain the true population mean. And to illustrate further the idea of the interval estimates, let's use this figure on your left side. Okay, so there are 10 random samples and there are 10 interval estimates for each sample. These are shown under the heading here, confidence interval, and the parameter is the population mean mu. This is the vertical line that indicates the location of mu, and the confidence intervals of 10 samples are here, the horizontal line segments. So let's note that some of these contain mean and some do not contain it. Okay? If there are more sample interval estimates and our confidence is 95%, in the long run, 95% of the sample confidence intervals will contain the mu. Okay, so on our previous lesson, we have learned about the properties of standard normal distribution. Okay, so now we're going to apply these concepts in estimating parameter values. On our previous chapter, we discussed about the standard normal distribution. So it is a normal probability distribution with a mean of 0 and a standard deviation of 1. At the horizontal base of the curve, we find the z-values. And the z-value or the z-score is the actual number of standard deviation that a particular x, remember what is our x? That is your random sample. value is away from the mean. So here on our left side, it gives us the area or decimal places under the standard normal curve for any z value from negative 3.49 to positive 3.49. And what do we call this again? This is the z table. Remember that the area under the curve is 1 or 100%. The proportion of the area between one standard deviation unit below the mean, so this is your mean, this is the one standard deviation below your mean, which is on your left side, and one standard deviation unit above the mean, which is the right side, is approximately 68%. So here, the middle 95% is the proportion of the region above, say, is equal to negative 1.96 and below z is equal to 1.96. So here, okay? Similarly, the middle 99% is the proportion of the area bound by negative 2.58 and positive 2.58. For another level of confidence interval, the corresponding z values can be found in your z table. So these z values are also called confidence coefficients or critical values. We also say that the standard normal variable z is the test statistics used to calculate the interval boundaries. We can also recall that for large sample values, the central limit theorem or CLT applies. That is, as the sample size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with mean mu and standard deviation sigma will approach a normal distribution. So when the sample size is large, applying the central limit theorem, approximately 95% of the sample means taken from a population with mean mu will fall within positive negative 1.96 standard errors of the population mean. This means that the interval estimate is given by here your mu minus 1.96 multiply by your sigma or your standard deviation divided by the square root of your sample size n to mu plus 1.96 multiply again by your standard deviation over the square root of your sample size n. Thus, if a sample mean is specified, there is a 95% probability that the interval will be mu or your mean minus 1.96 multiplied by your standard deviation over the square root of your sample size to the positive or the mean plus 1.96 multiplied by your standard deviation over the square root of your n, sample size n, contains a sample mean. Okay? In analogous manner, there is a 95% probability that interval specified by these figures. And this expression may be also stated like this. This expression shows that the interval estimate of the population mean is a number from the sample mean minus 1.96 multiplied by your standard deviation divided by the square root of your sample size n to the sample mean plus 1.96 multiplied by the standard deviation over the sample size n. So this is shown in the figure where z sub alpha over 2 is equal to positive negative 1.96 So the two z values and the positive 1.96 are the boundaries of the interval estimate. So here it is. Okay? Under the normal curve, the proportion of the area to the left, so here, to the left of negative 1.96 and to the right of 1.96 is sample mean minus 1.96 multiplied by the standard deviation of the square root of your sample size n is denoted by alpha. Okay, this is a Greek letter called alpha. Okay, in statistical analysis, we often use alpha to indicate our level of confidence. If the confidence is 95, then the alpha is the remaining 5% or 0.05. So here in this diagram, we have the 95% confidence level. And if we remember, the area under the curve is 100%, meaning we have 5%, okay, left. So since your standard normal distribution is symmetrical, therefore we have the other 0.025 on your left side and 0.025 on your right side. So this is the proportion of the area that is distributed in both tails of the standard normal distribution curve. This area is outside the boundaries of the interval estimate. So this is your interval estimate, and this is outside the area of your interval estimate. So the area that at each tail is here alpha divided by 2 or 0.05 divided by 2, which is equal to 0.025. This is indicated in this symbol. So Z Z sub alpha over 2. Okay? In the general formula. So the general formula for the confidence intervals for large sample is here. Okay? So the short form of this formula is the sample mean minus say sub alpha over 2 multiply by your standard deviation over the square root of your sample size n. Other confidence levels are also used in statistics like 90% or 99%. So in general formula, for determining the interval estimates for the parameter u or mu, the value x here, so the value of this is called the lower confidence boundary or limit, and the other value, this one, is called the upper confidence boundary or limit. For a 90% confidence interval, we use z sub alpha over 2 is equal to positive negative 1.65. For a 95% confidence interval, we use C sub alpha over 2 is equal to positive negative 1.96. And for 99 confidence interval, we use Z sub alpha over 2 is equal to positive negative 2.58. In the general formula for a confidence interval, the term here, say sub alpha over 2 times your standard deviation over the square root of your sample size n is called margin of error, denoted by E, which is defined as the maximum likely difference between the observed sample mean and the true value of the population mean. Thus, another way of writing this formula for finding the confidence interval for the population parameter mu is here, where your E is equal to the say sub alpha over 2 times the standard deviation over the square root of your sample size n. However, when your sigma is unknown, as it often the case is, the sample standard deviation S is used to approximate your sigma. Okay, so here, so the formula for the E is modified by this one, which we're going to discuss on the next lessons. The following rules is observed in computing the confidence interval for a population mean mu. So in rounding rule for a confidence interval for a mean, first, in computing a confidence interval for a population mean by using a raw data, round off to one more decimal place than number of decimal places in the original data. Second, in computing a confidence interval for a population mean by using a sample mean and a standard deviation, round off to the same number of decimal places as given for the mean. So the interval estimation procedure is summarized in the following four-step process. So first, describe the population parameter of interest. Example, your mean. Okay. Second is specify the confidence interval criteria. First, let's check the assumptions. Second, let's determine the test statistics to be used. Third, state the level of your confidence. Third, we're going to collect and present sample evidence. What are those? Collect the sample information and then find the point estimate. Lastly, we're going to determine the confidence interval. So to determine the confidence interval, we need to determine the confidence coefficients. What are those? That is your Z sub alpha over 2. We're going to find the maximum error of the estimate. We're also going to find the lower and upper confidence limit. And lastly, we're going to describe or interpret the results. Okay, so now let's have an example. So for example number 1, find the estimate of the population mean mu using the 95% confidence interval. For example number 1, we need to identify first the point estimates and what are the steps. So first, we're going to describe the population parameter of the interest. So we can say that the parameter, going to write this here, that the parameter of interest is the mean mu, where the sample purportedly belongs. So next steps, we're going to specify the confidence interval criteria. So first, we need to check the assumptions. So one, your standard deviation or the sigma is given. Next, the sample is normal. Let's put it here. The sample is normal as guaranteed by the central limit theorem. So the second step is to determine the test statistics to be used to calculate the interval. So the test statistics is the Z with your sigma is equal to 3. Okay. Next is we're going to identify the state we're going to state the level of your confidence. So the question asks for 95% confidence or the alpha 0.05. So this means that if more random samples were taken from the target population and an interval estimate is made for each samples, the 95% of the intervals will contain the true parameter value. So 95% confidence or your alpha of 0.05. So third step, we're going to collect and present sample evidence. So collect the sample information. The sample information we have is consists of your sample mean of 72 and sample size n of 120 and the standard deviation of 3. Lastly, we're going to find the point estimate. So, the point estimate for the population mean is 72, which is the sample mean. Now, we need to find the 95% confidence interval. In doing so, we need to determine the confidence coefficient. For this one, the confidence coefficient is 1.96. Second, we need to find the maximum error, E. And remember, the formula for that is E is equal to your Z sub alpha over 2 times your sigma over the square root of your sample size, N. And substituting the value, we have 1.96 times 3 over square root of 120. So, this will give us an answer of 1.96 multiplied by 0.27. So, the margin of error or the maximum error E is 0.53. Next, we need to find the lower and upper confidence limits. And to find that, so these are the formula. Okay? Alpha 2 over square root of your n x plus say alpha over 2 square root of your n. Okay, substituting the values, that will be okay minus 1.96 and then um 3 over square root of 120 less than your mean but greater than x 1.96 3 over. So basically, you're just going to substitute all the variables here. And then what is your sample mean? That is 72 minus what is the maximum error? That is 0.53. 2 72 plus 0.53. So therefore, we have 71.47 to 72.53. So lastly, we're going to describe the results. So therefore, we can say that with 95% confidence that the interval between 71.47 to 72.53 contains the population mean based on the sample size of 120. Okay, let's have the example number 2. A researcher wants to estimate the number of hours that 5-year-old children spend watching television. A sample of 50 5-year-old children was observed to have a mean viewing time of 3 hours. The population is normally distributed with a population standard deviation of alpha is equal to zero point 0.5 hours. So first, we're going to find the best point estimate of the population mean. Second, the 95% confidence interval of the population mean. So first, we need to find the point estimate, and the steps for that is first describe the population parameter of the interest. So the parameter of interest is the mean of the TV viewing of the 5-year-old children. So second step, we need to specify the confidence interval criteria. We're going to check the assumptions. Okay, so it says that the sample size of 50 children is large enough for the central limit theorem to hold. So the sampling distribution of mean is normal. Okay, let's put it here. So the sample size of 50 children is large enough for the central limit theorem to hold. Okay. So second step, so the sampling distribution. So the sampling distribution of means is normal. So the second step is to determine the test statistics to be used to calculate the interval. So the test statistics is the Z using um, zero point 0.5. So next, we're going to state the level of confidence. So the question asks for 95% confidence or an alpha of 0.05. So this means that if more random samples were taken from the target population and an interval estimate is made for each sample, the 95% of the intervals will contain the true parameter value. So for our third step, we're going to collect and present sample evidence. So the sample information consists of your sample mean is equal to 3, which is the 3 hours, your sample size of 50, okay, so 55-year-old children, and a standard deviation of zero point 0.5. Next is we're going to find the point estimates for the population mean. So the point estimate for the population mean is 3. Why? Because it's the sample mean. Now, we're going to find the 95% confidence interval. So first, we're going to identify the confidence coefficients. And the confidence coefficients is 1.96. Next, again, we're going to find the maximum error, E. So the formula for that is E is equal to your Z sub alpha over 2 times your sigma over the square root of your sample size n. And then substituting these values, we have 1.96 multiplied by 0.5 over square root of 120. So 1.96 times 0.07. So your maximum error is 0.14. So next, we're going to find the lower and upper confidence limit. So the formula for that is again here, minus alpha over 2 square root of n less than your mu but greater than, okay, and substituting these values. So our sample mean is 3 minus 1.96, 0.5 square root of 50. I'm sorry, this one is 50. Okay. um, 3 plus 1.96 per 0.5 over square root of 50. Okay? And 3 minus 0.14 to 3 plus 0.14. So therefore, 2.86 to 3.14. And lastly, we're going to describe the results. So we can say with 95% confidence that the interval between 2.86 hours to 3.14 hours contains the population mean based on the 80 based on the 55-year-old children's TV viewing time.